Well, let's have a look at the model of user requirement and context. There are typically several interested parties in the design and construction of systems. These include the clients, who commission the development, the designers and developers, who design and build the system, and their management, who look after the running of the project. These people are primarily interested in what the system should do, its functional requirements. An important set of people who are often forgotten about are the users, who will actually end up using the system. In order to build systems which users will find usable, we need to consider their needs rather than exclusively concentrating on functional requirements of the system. These non-functional requirements include issues such as the usability of the system and how acceptable it is to the users. Without such considerations, systems may be produced which have been designed without considering whether they would be acceptable to users. Let's have a look at an example. The introduction of an automated ordering system at a restaurant may not be acceptable to the users, waiters, if it requires them to spend a large proportion of their time interacting with it, rather than interacting with restaurant goers. Clearly, if users do not find a system acceptable, they will be reluctant to use it, and so extensive redesign or user retraining may be necessary, costing large amounts of time and money. The rest of this section looks at approaches which are considered user-centered. That is, they focus their attention on the user and their non-functional requirements, rather than concentrating solely on functional requirements. Let's now have a look at the socio-technical models. It considers the users within the organizational context that the system will be introduced into. The particular focuses on the interplay between the social and technical issues, hence the term socio-technical. One such approach is custom, which concentrates on identifying who will be involved with the new system and what their requirements are, not just functional requirements. Once these have been identified, the designers of the system should have a better grasp of the non-functional user requirements, as well as the organizational structure itself and how this relates to the design. Taking these requirements into account should help designers develop more acceptable and efficient systems. Custom refers to the people who would in some way be involved with the new system as stakeholders, who can be classified in 4 ways. Primary, the people who will use the system, for example, the waiters in a restaurant. Secondary, people who produce input for the system or receive output from the system but do not directly use it, for example, the restaurant goers, who are presented with a bill produced by the system at the end of their meal. Tertiary, people who are touched by the success or failure of the system but are neither primary nor secondary stakeholders, for example, the owner of the restaurant chain. Facilitating. Once the stakeholders have been identified, their characteristics are analyzed to develop user-centered requirements for the system. Let's see what are the questions that were summarized to analyze stakeholders' process. What does the stakeholder have to achieve, and how is success measured? For example, waiters have to ensure dinners are served at appropriate times and are happy with the level of service. What are the sources of dissatisfaction and stress? E.g., for a waiter, this may be the pleasure of serving food and providing a pleasant eating atmosphere. They may be stressed by angry customers or a large number of customers to keep happy at the same time. What knowledge and skills does the stakeholder have? E.g., a chef has extensive knowledge of cooking, which the waiters may not. What problem can be caused? E.g., the owner of a chain of restaurants may be a technophile whilst a chef may be a technophobe. This may well cause conflict in the introduction of new technology. Are there any workgroup attributes that will affect the acceptability of the product to the stakeholder? E.g., is there something about people who become waiters that will affect how well they accept the product? What are the choice of actions? E.g., a busy waiter will typically have to perform many fragmented tasks with high frequency in order to keep the diners happy. Does the stakeholder have to consider any particular issues relating to responsibility, security, or privacy? e.g. waiters may need to be discreet with regular diners, who dine each night with a different partner, and may need to ensure that credit card payments are dealt with securely. What are the typical conditions in which the stakeholder is working? E.g. the chef of the restaurant typically works in a hot and dangerous environment, whereas the owner of the chain of restaurants may work in a conventional office environment. Soft Systems Methodology, SSM, takes a broader view than socio-technical approaches by considering the organization as a whole. From this perspective, the stakeholders and technology are components of the larger context. As with other user-centered approaches, the intention is to understand the context of the people involved with the system, rather than making explicit design decisions. These models of the situation are instead used to inform and help designers understand the context in which the final system will fit. SSM involves the development of three kinds of models to help understanding the organizational context. The first kind of model is referred to as the rich picture, which provides a detailed description of the problem situation. This includes details similar to the models of stakeholders developed in socio-technical approaches discussed previously: who the stakeholders are, what groups they work in, and what tasks they perform. The organizational structure could be developed from interviews with people in the organization, observations of their work practices, or more interactive approaches, such as workshops, in which stakeholders act out situations in order to help explain their work context. The next stage moves the focus of analysis from the real-world situation to the development of definitions of what stakeholders perceive to be the activities taking place in the organization. These definitions are referred to as root definitions of the system. There may be several different root definitions which need to be reconciled at a later stage. Click on the button to view the aspects of the root definitions model. Clients, people who benefit or accept output from the system. For example, in our restaurant, the clients may be the diners, who benefit from the restaurant nutritionally and receive output from the system by way of a bill. Actors, stakeholders who perform activities in the system, for example, the waiters and chefs in the restaurant. Transformations, what changes the system performs on things in the environment. Worldview, how the system is perceived by a client. For example, a waiter may perceive an automated billing system as beneficial, as it reduces the work they have to do in maintaining the bills for multiple diners. Owner, who the system belongs to and who can allow changes in the system. For example, the owner of the restaurant chain owns the automated billing system. Environment, what factors influence the system. For example, a restaurant has to abide by certain health and safety standards. Finally, a conceptual model is constructed, which details what the system has to do to meet the root definitions. The most important part of the root definitions are the transformations, which are used in the conceptual model to define what is achieved and how it is achieved. These achievements are usually modeled hierarchically to provide different levels of detail, much as tasks are decomposed in task analysis. For example, the overall achievement of serving a diner includes successfully finding out what the diner wants, serving them, clearing the table, and ensuring that the food is paid for. Considering the hierarchic structure, achieving payment for the food involves several sub-achievements, such as producing the bill, collecting the money, and possibly producing a receipt. The conceptual model is used to identify differences between the real-world situation and the model of how the stakeholders perceive the system. These differences can then be used to inform change and/or development of appropriate systems. The key outcome of the whole SSM approach is for designers to have a better understanding of the context in which developed systems are to be placed. The two approaches we have looked at so far develop user-centered models which are typically used in the early stage of system development. In contrast, participatory design aims to keep the whole process of developing a system user-centered. This is achieved by including users in the design team, rather than treating them as subjects of analysis who remain outside the core design situation. The motivation for this is that users are essentially experts on their work situation. They know full well what work they do, how the organization works for them, and who they need to work with, and so including them in the design process is essential if the new design is to fit well into their context. Moreover, the introduction of new systems typically changes the work context. For a new system to be acceptable, these changes in the work context also need to be acceptable. Having users in the design team should help ensure that these changes do not overly disturb other users. Participatory design has three main characteristics. Work-focused, perform, rather than focusing on the system requirements. Collaboration, the designers and users collaborate on the design so that the users can contribute at every stage. Iterative design does not just happen once. The emphasis of participatory design is on several design and evaluation stages which build to a final design. As participatory design focuses on the collaboration between users and designers, it needs to employ various techniques and models to communicate ideas between them, and these include brainstorming sessions in which users and designers generate a range of ideas which are developed without judgment. These ideas are then fed into other techniques to be developed further or dropped. Storyboarding. The storyboard models user activities as a series of drawings, a little like a comic strip description of the activity. They are simple to develop and help users communicate with the designers about what they do and how they do it. Workshops. These provide a forum for discussion in which designers and users can ask each other about their perspectives and so establish common understandings of the design issues as well as focusing their views of the design. Typically, they are used to fill in gaps in understanding. Users ask about technological possibilities. Pencil and paper activities. This provides a more interactive way of talking through designs than storyboards. Typically, rough designs are drawn, i.e. possible designs are modeled using pencil and paper, and then users consider how they would use it by moving through the design, step by step. Problems with the design can then be identified from the trouble the users have as they move through it. These problems can then be addressed in the next iteration of the design. As we discussed at the start of this unit, a model is a representation of something that we can easily work with. In the previous section, we looked at models of user requirements, essentially, models of the cognitive abilities. That is, rather than looking at the context in which users work, we will consider models of how people behave. These cognitive abilities which can be used to inform design, and, as we shall see in Unit 9, to evaluate systems. In this section, we look at two cognitive models, GOMS and ICS. Let's have a look at a brief overview of GOMS. GOMS uses an explicit model of cognitive processes developed from studies of users. GOMS itself stands for goals, operators, methods, and selection rules. This core set of concepts describes the tasks that users perform and how they achieve them. GOMS is more than just a way to describe tasks, though. It provides a family of modeling techniques which can be used to generate predictions of the time to complete tasks, given descriptions of the tasks and their user interfaces to be used. These predictions are based on a simple model of cognition called the Model Human Processor, MHP, and have an absolute accuracy of between 10% and 20%. The basic assumption of GOMS is evident in its name, that users understand their goals. GOMS considers the actions to meet such goals. Having made this assumption, GOMS can give us feedback on the coverage and consistency of the user interface. By coverage we mean whether the user interface contains the necessary functionality to support the tasks it was designed for. Consistency refers to whether similar tasks are performed similarly with a user interface. Moreover, GOMS can give an indication of whether frequent goals can be achieved quickly using the given interface. Now let's move on to Model Human Processor. The central part of GOMS is the Model Human Processor, MHP. This is a simplified view of the psychological processes involved in human cognition, which can be used to make approximate predictions of user behavior. Even though it is based on psychological evidence and the motivation theory for the MHP is that it should be usable by non-psychologists, for example designers and evaluators. The MHP consists of set of processors, systems which process information and may make decisions. Set of memories, areas in which information is stored in various forms by processors. Set of principles of operation, these guide the operation of the processors and are crucial to a realistic account of human behavior. The MHP itself is divided into three interacting subsystems: the perceptual system, the motor system, and the cognitive system. Each of these subsystems has their own memories and processes, and works on different kinds of information, as illustrated in the following diagram. Perceptual system, input from the eyes and ears are stored symbolically in visual and auditory image stores, which go on to be processed in working memory by the cognitive system and possibly stored in long-term memory for later access. For example, the sound of a car horn is coded as a loud warning. Cognitive system processes information from working and long-term memory to make decisions about how to respond. For example, processing the fact that there is a loud warning noise, recalling that evasive action should be taken in such situations, and deciding to run to the pavement. Motor system executes responses to decisions made by the cognitive system. For example, running to the pavement. Click on the button to see a model of the MHP. Here is the Model Human Processor, MHP. Each component of these systems has parameters which are used in the generation of behavioral predictions. Each memory system is defined in terms of its storage capacity, how many pieces of information can it hold at one time, and the decay time of an item, how long is it before an item is forgotten. Similarly, each processor is defined in terms of processor cycle times and how long it takes to process one piece of information. Goals are something that the user wants to achieve. For example, go to airport, delete a file, or create a directory. They have a hierarchical structure, that is, they are composed of many sub-goals which need to be achieved to meet the larger goal. These are similar to the goals identified in task analyses. Operators are elementary, cannot be decomposed into smaller operations, perceptual, motor, or actions used to accomplish goals, or actions that the software allows user to make. For example, to move a file to a different folder, the user might perform the following operations: move cursor to item, hold mouse button down, locate destination icon, let go of mouse button. From operators, we build up methods which are sequences of steps that accomplish a goal, and so are like tasks in a task analysis. See Unit 8. As with goals, these methods can include other sub-goals. A fundamental assumption in GOMS is that methods are learned and routine, so no problem solving involved, and that there is only one way a user stores knowledge of a task. For example, a user moving a file to a different folder could be described in GOMS as goal, move file to a different folder, method, move file, operators, move cursor to item, hold mouse button down, locate destination icon, let go of mouse button. If there is more than one method to accomplish a goal, the selection rules tell you which method to use. Again, as with methods, they assume error-free performance. If condition, then, accomplish, goal. Press the button to view an example. Here is an example. If restaurant accepts credit cards, then pay by credit card, else, if restaurant accepts checks, then pay by check, else pay by cash. ICS is an elaborate framework which assumes that human perception, cognition, and action can be analyzed in terms of discrete, interlinked information processing modules. In contrast to GOMS, ICS is a much richer way of modeling human cognition, as we shall see in this section. Each subsystem of ICS is independent and operates in a specific domain of processing, of which there are three main components: sensory, visual, and auditory stimulus, representational, representations of information, effector, body movement. Although each subsystem operates in different domains and on different kinds of information, they all share a common structure. Let's see a model of ICS subsystems. Each subsystem has an input to its left and one or more outputs to its right, as well as its own memory record and a set of transformations. All information which is input to the subsystem is stored in the memory record and can at a later point be used as an input to the subsystem. The outputs depend on the transformations which transform information from one form to another. In the example, we have three transformations which transform the input information into three different codes, X, Y, and Z. A good point to start understanding ICS is by considering the visual subsystem illustrated in the diagram, which forms part of the sensory domain. The stakes input from the eyes in the form of sensory representations with information about edges, angles, shades, contrasts, hues, etc., and transforms it to object representations with information about depth, position, orientation, shapes, etc. Note that a copy of the visual representation is stored in the memory record for later use. Note also that the clarity of the visual representation alters the success of the transformation to an object representation. It is important to remember that these two representations, visual and object, are both mental representations, but at different levels of information. Here is a diagram of the complete ICS framework. The visual subsystem, VIS, just described, can be seen in the bottom left of the diagram, in the sensory domain. That is, input from the sense. We need to further process information to extract meaning and make decisions. For example, we may need to interpret the gray pentagon as a 50-pence piece, and then use it appropriately. Of course, there is plenty more processing involved in locating the text on the screen, positioning the cursor, reading the menu bar, etc., but this description gives an idea of the processes involved.